Okay, in this final video on proteins, we're going to look at polypeptide synthesis, and actually I'll just qualify that. We're going to look at dipeptide synthesis, and you're just going to have to infer that the methods that we use to make a dipeptide could be used to make a tripeptide, a tetrapeptide, or a polypeptide, or whatever. Okay, so let's look at the reaction that's at the crux of peptide synthesis, and that's the reaction of a carboxylic acid with an amine to make an amide. Okay, you can actually do that reaction by just taking the salt right here that you get from mixing a carboxylic acid and an amine and just heating it to a very high temperature. If you do that, you'll make an amide and water will be released. However, that's not a very mild method for doing that. All right, so a reagent that's been developed specifically for this purpose is this reagent right here called dicyclohexylcarbodiamide, okay, abbreviated DCC. All right, so if you treat a mixture of a carboxylic acid and amine with DCC, you will generate under very mild conditions, right at room temperature, you'll make an amide, and you won't make water, you'll actually make this byproduct here, dicyclohexylurea, which if you look at dicyclohexylurea, if you look at its molecular formula, it's merely the product for reaction of DCC with water, okay? If you take the formula for DCC and add H2O to that formula, you get the formula for dicyclohexylurea. All right, so let's look at the mechanism. All right, the first thing that we're going to do is we're going to take DCC and a carboxylic acid and we're going to transfer a proton to nitrogen, okay? All right, so this is going to make this activated aminium salt. Okay, this functionality right here is just an aminium salt, so you can add a nucleophile to that, and this gives you this species here, which is like an anhydride in its reactivity. Okay, so it'll now react with the amine just like an anhydride would, by nucleophilic acyl substitution. First, the lone pair is going to add to the carbonyl group, like you see here. It's going to make the tetrahedral intermediate here. The better leaving group is this group over here. Let's see, first we're going to actually move a proton over to here, and this set of arrows that you see here will directly produce the amide and the urea. Okay, all right, so now we have a very mild method for treating an amine and a carboxylic acid, or mixing an amine and a carboxylic acid together and making an amide. All right, so problem solved. All we have to do is take two amino acids. So let's say we want to make alanine is the N-terminal amino acid, valine is the C-terminal amino acid. Very simple. We're just going to take the free amino acids and some DCC and mix them, right? Turns out we're going to actually get some of this product, but this is not really a good method, all right? Not only are we going to get alanine valine, we're also going to get valine is the N-terminal amino acid and alanine is the C-terminal, so we're going to get the opposite regiochemistry. Okay, so there's nothing to prevent this amine from attacking there. These are not mechanism arrows, these are just what goes where arrows, or that nitrogen from attacking there. All right, so those are our dipeptides. Not only do we have two different amino acids coming together, there's nothing under these conditions to stop two alanines from getting together, and there's nothing to stop two valines from getting together. All right, And another issue here, there's nothing to stop this reaction at dipeptide synthesis. We can make tripeptides, tetrapeptides. Alanine and valine have free carboxylic acid groups and free amine groups, even as the dipeptide. Okay, so amino acid or protein synthesis or dipeptide synthesis is a little bit more complex. All right, so the reason that we are making the opposite regiochemistry here, or the isomeric peptide, is because we can't control which amine reacts with which carboxylic acid. Ideally, we want this to be the C terminal, this to be the N terminal, and we need for basically for this compound, for this nitrogen here, it needs to be unreactive. Okay, and this carboxylic acid group also needs to be unreactive so that it isn't part of the amide. Okay. All right, so what we have to do is we have to take the N-terminal amino acid alanine, and we need to protect that. And we need to take the C-terminal amino acid valine, and we need to protect its carboxylic acid group. So we're going to protect the nitrogen of alanine, the N-terminal amino acid, so that that nitrogen doesn't become part of the protein chain, okay, or doesn't become part of an amide bond. And we need to protect the carboxylic acid group of valine so that that carboxylic acid group does not become an amide. All right, so the ideal choice here is the T-butyl oxycarbonyl group, collectively known, as we saw in a previous video, as a Bach group. Okay, this is ideal because the conditions to remove this group are very mild. Okay, all right, so what we're going to do is we're going to take the free amino acid, alanine, treat it with this reagent here, which we've already seen before in the presence of the base triethylamine, and this is going to install the Bach group at the nitrogen of alanines, and we're going to end up with this compound, which we're just going to abbreviate Bach ala. All right, for the C-terminal amino acid, we're going to protect the carboxylic acid group as an ester. Okay, and we're just going to use the Fischer Esterification to convert the free amino acid valine into the corresponding ester. And we're going to choose a benzyl ester here for its easy removal as well. All right, so when we mix these two compounds, there's only one amino group available, that one, and only one carboxylic acid group available. So this is what we get. We get the product from that nitrogen reacting with this carboxylic acid group, or let me just say this nitrogen reacting with this carboxylic acid. All right, DCC is going to now give us a dipeptide, but the dipeptide is going to have these protecting groups on it, the Bach here and the ester here. And this is important because we don't have in this molecule any free amine groups or any free carboxylic acid groups. So we can't get any longer chains than the dipeptide that we've constructed here. So all the products that we get are going to be dipeptides when we protect these units. Okay, the Bach group, owing to the stability of the tertiary butyl cation, can very easily be cleaved with this reagent here, trifluoroacetic acid, at room temperature. Okay, and this is going to remove the Bach group from nitrogen to now give us the dipeptide with, protected as its ester. And the ester can be removed either through hydrolysis, okay, and an ester is much easier to hydrolyze than an amide, so it's very easy to hydrolyze the ester to remove it without cleaving the amide group. But the choice of the benzyl was actually very fortunate here because the benzyl can be removed in a hydrogenation reaction. So the hydrogenation reaction will we'll just simply remove the benzyl group. It'll actually turn it into toluene or methylbenzene, and this will give us now the dipeptide that you see here. And this dipeptide, of course, corresponds to alanine valine, okay, and that is that structure right there. Okay, so here's a problem for you. I always put one of these types of problems on the exam. Design a synthesis of met-val from the free amino acids. Note here that methionine is the N-terminal amino acid and valine is the C-terminal amino acids. You have to design a synthesis that's going to produce met-val and not val-met. Okay? All right, so since methionine is the N-terminal acid, in the DCC reaction, we have to have its nitrogen protected. Since valine is the C-terminal amino acid, its carboxylic acid group has to be protected in the DCC coupling. All right, so we're going to, sorry, I got the animation backwards. Initially protect the N-terminal amino acid with Bach or carboxybenzyl. We're going to just use Bach here. There are a lot of alternatives to Bach. You can take a course in organic synthesis if you want to look at a lot more a lot of the different protecting groups you could select, but Bach is probably the most common one that we're going to use. All right, so we're going to turn methionine into the Bach derivative, and we're going to turn valine into the ester derivative, and these two are going to be prepared in steps 1 and 2. And finally, we're going to couple them. And that's going to give us, again, the Bach-protected free amine group in our dipeptide and the carboxylic acid-protected ester group for the C-terminal amino acid. All right. So we just need to remove these protecting groups. This time I've used an ethyl ester, so our only option is to use base or acid hydrolysis to get rid of it. We're going to remove the Bach group with trifluoroacetic acid, and we're going to remove the ester group by just doing an ester hydrolysis under conditions that are mild enough to hydrolyze the ester without hydrolyzing the amide. And pretty much if you do this at room temperature using 1 molar base, that's not nearly harsh enough to cause the amide to hydrolyze. Okay, all right. So how would we make insulin, for example? Let's have 51 amino acids. We're looking at in the direct sequence here, after we've put the protecting groups on, we're looking at 3 steps. All right, and if we did this 51 times, that would be 153 steps. Let's say we're getting a 90% yield each time we do that. Do your calculator with 0.9 to the 153rd power, and you would see a rather minuscule number. Okay, so 90% is a good yield, but not over 153 different operations. Okay, all right, so a better method had to be developed, and this won the Nobel Prize a few years ago. This is the Merrifield solid phase peptide synthesis. Okay, so what we're going to do is we're going to bind the amino acid to a solid support. Okay, all right, so what we're going to do here now is make an ester from this polymer that has benzyl alcohol groups on it. Okay. Okay, so we're going to make an ester from this alcohol group and this carboxylic acid group. This is going to produce this. And the beauty here now is that since it's a polymer, it's not going to dissolve in anything. So the purification is just merely washing and filtering. Okay, so we don't really lose any material that way. All right. Once that's on the polymer support, we'll remove the protecting group. We'll now add a different amino acid. This gives us a dipeptide, and we can cleave the Bach group here. Okay, actually, sorry, we don't. All right, sorry, that actually, this was correct. Sorry about that. Yeah, so this is how we're going to release it in the end to make a dipeptide. But if we wanted to make a tripeptide, what we would do is we would just cleave off this Bach group right here, and we could add another amino acid. Okay, so what's been developed is actually a machine where it's known exactly how long you have to expose it to trifluoroacetic acid, how long you have to expose it to DCC. All of the 20 amino acids are commercially available as their Bach derivatives. You don't even have to really make them. You basically just put a bottle of reagent with a tube going into the machine from each of the 20 amino acids. You just program it to what sequence you want, and then it does all the work for you, and you come back later and then collect your protein. Okay, so this is turned out to be a totally automated process, and because the purification steps are merely washing and filtering, there really is very minimal material loss in each step. So you don't really have, you can do 153 reactions and just sit at your desk reading a book while or whatever you do, or playing a video game or whatever, while the machine does all those 153 reactions for you if you wanted to make insulin. Okay, so that's where this video is going to stop. This is actually the last video in the second half of the organic chemistry class. Okay.